Hello everyone. Today's video and the next will be dedicated to applications of the orthogonal projections that we studied last time. As a brief reminder, what we mean by an orthogonal projection is something like the following setting. You have a subspace W inside Rn, and you have a vector U inside Rn. You can then decompose U as the sum of two vectors, little w and z, that have the property of belonging to W and being perpendicular to W, respectively. The properties of this decomposition, called the orthogonal decomposition or the orthogonal projection, is that W is the closest vector in the space capital W to U, and that there is a projection associated to a matrix called the projection matrix that associates to every vector U the corresponding vector W. This matrix is given, we computed it last time, as with the following expression, C times C transpose C inverse C transpose, where C is a matrix whose columns are a basis for the space W. The first application that we'll see today is that of least square approximations. The problem is the following. Imagine you have a data set, which are the red dots in this picture, and you want to find some shape that best mimics that set. In this particular picture, we would like to approximate that set with a line, which I'll denote like so. It's the green line. We don't know exactly what parameters are A1 and A2, and that's exactly the problem. What we want to figure out here is how to find the line that best approximates this data set. So we want to find A0 and A1 that are optimal in the sense that they minimize the mistake you make by considering the green line instead of points in your data set. To do so, we will need to consider the distance of every one of these points to the line. I'll denote those DIs, and by looking at how it's set up in the picture, DI is the difference between YI, which is the Y coordinate of the point in the data set, minus the Y coordinate of the point on the line at that point, which is A0 plus A1 XI. So this is the distance of one single data set I to the line Y equals A0 plus A1x. Then the next thing we'll do is to build a vector whose entries are all of these distances, all of these errors we're making in approximating the data with this line. And then we take the length of that vector, capital E, which is just the sum of the squares of these errors. You can think of E as some quantity that measures how off is our approximation with a line from the data set. And the goal of the problem is that of minimizing E, finding A0 and A1 that minimize E. In fact, E does depend on A0 and A1, because if I explicitly write out what we're doing here, the components of E are Y1 minus A0 plus A1 x1 all squared plus Y2 minus A0 plus A1 x2 all squared, and so on up until the end. So it is a function, well, it will depend on our data set because there's y's in here, but it will depend most importantly on the choice we make of A0 and A1. So as I said, the goal is to find A0 and A1 that make this E as small as possible. This is how we're going to set the problem up. We'll define a vector Y, Y1 through Yn, with all of the Y coordinates of the data set. And then we define a vector V, whose entries are the coordinates on the green line. Entries of V are the Y coordinates of these bright green points that I'm drawing here. Those are the entries of my vector v. It's written as a0 plus ax in all of its entries, but I can rewrite it more explicitly like so. Every entry has a0 and then as a1 times x1, x2, and so on up until xn. So I'll call these two vectors v1 and v2. Now, it's easy to see that v1 and v2 are linearly independent. This is a vector in which every entry is constant and is equal to 1, and this is not. So since they're not multiples of one another, they're linearly independent. And therefore, v lies in the span of v1 and v2, which we'll call w. And v1 and v2 is a basis for w. So conceptually, what we're doing is that we're saying that all of the possible choices of lines that interpolate our data set, which sit inside the choice of a0 and a1, correspond to choosing exactly one vector inside w. So all of the vectors in w are a choice of a different line that interpolates the points. And what we're computing here is our error quantity e, which is nothing but the length of y minus v. Let's take a look at it again. Every summed in here is the entry of y minus the entry of v corresponding to it, squared, and then you sum them together and you take a square root. In other words, what we're doing is measuring in e the distance between the two vectors y and v. Minimizing this distance by the properties that we just recalled is the same as saying that the vector v is the projection of the vector y onto the space w, because the projection is that vector that minimizes the distance. And in this case, distance is error. Okay, so now we have information about what v should be, because we know that v should be the projection onto w. Let's compute it. V is the projection onto w, that's what's written here. Then to do that, remember what we want to do is to set up the projection matrix, starting with a matrix whose columns are a basis for the space w, which is, in this case, is given by v1 and v2 by our construction. And another fact that you have to remember is that v is this optimal point choice, but also by what we've written here, v is exactly a0 v1 plus a1 v2. In other words, I can write v as a v1 plus b v2, where a and b are the optimal choices for a0 and a1. So v is c times the optimal choices that we're looking for. Remember that figuring these out is our goal. Finding these is our goal. Those are the best fitting parameters. Okay, so how can we proceed? Well, let's take a look at this. PW, we computed it last time, is C times C transpose C inverse times C transpose, and then multiplied by Y. And we just said that V is C, we leave a little bit space here, C times the vector AB, which is what we're after. Now, one thing that we can do is multiply both sides by C transpose here, so that then I have C transpose C inverse, so these go away. And what I'm left with is the following. C transpose Y is C transpose C AB. I can multiply again by C transpose C inverse on both sides, and I get the following. AB will be given by C transpose C inverse times C transpose Y. And now let's take this moment to look at this. After this manipulation, we expressed our optimal choice AB of parameters, of fitting parameters, as in terms of Y, which is a vector that is given by the data set, and C, which is a matrix that we computed. It's given by V1 and V2. So that gives us a formula for the best fitting line. Let's have a look at an example of this. Here's a data set with 5 points. Our vector Y is the vector whose entries are the Y coordinates of the data set points. So it will look like this: 13, 10, 17, 15, 20. V is the vector that has A0 in all of the entries here, because the entries of V are A0 plus A1 xi. The X coordinates of the data sets are 1, 2, 3, 4, and 5. So that's my vector V2. These two vectors together give me the matrix C, which is 1, 1, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5. Notice once again that these are linearly independent. So they are a basis for the column space of, they're a basis for the span of V1 and V2. Okay, let's apply our formula, what we just computed up here. The optimal parameters are CTC inverse CTY, which is nothing but what I've written here. Takes a little bit of computation, and maybe you want to use a calculator to do this, but you can just sit down and do it. You compute first C transpose C, and you get this matrix 5, 15, 15, 55. You invert it, and then you punch that in front of C times Y. The result you get is this vector 5.3 and 3.9, which tells you essentially that the best fitting line for that data set is the line of slope 3.9 and y-intercept 5.3. Of all the possible lines that best fit this data set, the one that does it better, that is overall closest to the data set, is the line given down here. Let's have a look at one other example, an application of this process. Maybe I haven't mentioned it, but the reason why this is called the method of least squares is that we are minimizing the vector whose components are, we're minimizing a quantity whose components, whose summands are the squares of the distances. And that's why this method is called of the least squares. Okay. Let's go back to the example. The second one, this time we want to interpolate a data set using a parabola instead. If we use a parabola, then there's one extra parameter. We have A0, A1, and A2. Because the general parabola looks like this: A0 plus A1x plus A2x squared. In other words, the setup will vary slightly in that Y will still be the same principle. It will contain the Y coordinates of the data set, 13, 10, 17, 15, 30, 30, 60. But V will be given by the entries. Well, the entries of V will be given by the Y coordinates of the green points that I'm highlighting now. So for every coordinate xi down here, you will have that the corresponding entry of V will be A0 plus A1 xi plus A2 xi squared. In other words, you can write V as it's written here. A0 with a vector of ones, A1 times a vector of variables, and A2 times a vector of variables squared. I want to remind you here that we have seen a behavior similar to this when we looked at Vandermonde matrices and Vandermonde determinants. These matrices here add a column of 1, and then a column of variables, and then a column of variable squares. This method of least squares is one of the applications of the Vandermonde determinants. we won't use it here, but if you want to develop this method further, then you'll have to use those. Okay, so once you get to this point, you get a matrix C, which is given by the 3 columns of your entries, which are, how many data sets are there? 7. 1, 2, 3, 4, 5, 6, 7. And then we have 1, 2, 3, 4, 5, 6, 7. And then you have the squares, 1, 4, 9, 16, 25, 36, and 49. That's our matrix C. And then again, as before, the optimal vector A will be given by C transpose C inverse times C Y. Now this time, this computation is a little longer, so I solved it using a computer program. You see, I used was it Python? I think it was Sage. I defined the matrix like this, and then I just and the vector y. Then I just did one simple computation. Here I computed C transpose C inverse, and then I inputted the formula for this vector A. When you print it out, you get that these parameters are the ones that provide you with the best fitting data. In other words, the best fitting parabola has equation y equals 145 over 7 plus x times, oops, I guess, minus 365 over 42x plus 41 over 21x squared. Okay, in the next video, we'll see other applications of the projection matrices.